All right, let's just jump right in. If you've ever found yourself wondering exactly how scientists predict the precise fraction of a second a falling object will hit the ground, or, how civil engineers figure out the exact speed limit for a school zone so you can actually stop in time, well, you are definitely in the right place. Today, we are unpacking this explainer on Chapter 2, Motion in a Straight Line. It's all about the fascinating physics of how things move.
So here's our roadmap for the explainer today. We're going from the absolute cosmic scale of the universe right down to the practical, everyday physics of surviving your daily commute. We've got 5 parts: the universality of motion, capturing the instant, the kinematic toolkit, gravity and freefall, and finally, physics behind the wheel. Let's get to it.
Section 1. The universality of motion, from galaxies to blood vessels.
To kick things off, let's zoom all the way out to establish one really simple fact. Motion is common to absolutely everything in the universe. Now, in physics, kinematics is basically the study of how to describe this motion without getting bogged down in what actually caused it. And to keep things super focused today, we're looking specifically at rectilinear motion. That's just a fancy way of saying motion along a straight line. And you see it everywhere, right? Whether it's the sheer macro scale of the sun moving within the Milky Way or the Earth rotating, or even the micro scale of blood flowing straight through your arteries while you sleep. We see it in water rushing down a dam or leaves falling straight down from a branch. Now here's a cool trick. In kinematics, as long as the size of these objects is way smaller than the distance they're moving, we can just treat them as tiny, dimensionless mathematical points. Seriously, treating a massive, spinning, incredibly complicated object like the Earth as just a single dot on a graph, it makes calculating its journey through space a whole lot easier for physicists.
Moving right along to Section 2, Capturing the Instant, the Calculus of Speed.
What's really fascinating here is how we transition from tracking motion over a big long trip to pinning it down at an exact millisecond. Obviously, if we want to describe motion, we have to talk about velocity. But velocity isn't just one static thing. Average velocity is great and all if you're just tracking a road trip. It tells you how fast you moved over a big chunk of time, but it completely fails to tell you how fast you are going at any one specific instant. To truly understand motion, we have to bring in calculus to capture the instantaneous velocity. We literally have to look at what happens when the time interval mathematically shrinks down to 0. This concept right here gives us the exact mathematical precision we need. It effectively captures the exact rate of position change at any given fraction of a moment. Think of it like pausing a video frame by frame. You're isolating a specific millimeter of movement in a tiny fraction of a second. It is literally the ultimate speedometer reading, completely frozen in time. And bringing time into the mix brilliantly illustrates why acceleration is measured over time, which, by the way, was a puzzle that completely stumped brilliant scientists before Galileo came along. Early on, people just assumed acceleration was the rate of change of velocity with distance. The further you fall, the faster you go, right? Makes intuitive sense. But Galileo actually studied falling objects and realized something completely counterintuitive. During freefall, velocity changes with time, not distance. Every single second you fall, you gain the exact same amount of speed. So acceleration is strictly defined as the rate of change of velocity with time.
Section 3, the Kinematic Toolkit, the rules of rectilinear motion.
So the crucial takeaway here is that if acceleration stays constant, we can build a really simple, powerful mathematical toolkit to essentially predict the future of a moving object. Our first kinematic equation is wonderfully straightforward. It tells us exactly what the final velocity will be if we know our starting speed, our acceleration, and how long we've been moving. Think of merging onto a highway. If you start at a certain velocity, v0, and you accelerate smoothly at a rate a for t seconds, your new velocity is literally just your starting speed plus the extra speed you've picked up over those seconds.
Now, the second equation takes it a step further. It maps out the precise distance you cover over that time. The distance x you travel isn't just your starting speed multiplied by time. Because you're accelerating, you're actually eating up extra ground every single second. That compounding extra distance, that's exactly what that 1/2 a times t squared calculates at the very end of the equation. And our final equation? This is basically the ultimate shortcut. It links speed, acceleration, and distance without even needing to know the time. It's kind of like unlocking a cheat code in physics. By combining the first 2 equations to eliminate t, we get this incredibly powerful formula. Your final velocity squared equals your initial velocity squared plus 2 times acceleration times distance.
Okay, moving to Section 4, gravity and freefall, nature's constant acceleration. Let's see how our new toolkit applies to the most universal example of constant acceleration we have, gravity. Everything we just talked about can be directly applied to an object just dropping out of the sky. Assuming negligible air resistance, every single object in freefall near Earth's surface accelerates downward at a constant 9.8 meters per second squared. We just call this g. It literally does not matter if you drop a tiny pebble or a massive boulder. Nature applies this exact same constant acceleration to absolutely everything. And because it's perfectly constant, our kinematic toolkit works flawlessly here. And check this out. This structured breakdown beautifully showcases Galileo's law of odd numbers. It proves that a falling object covers distances in a perfectly expanding ratio of 1 to 3 to 5 to 7. What does that mean? Well, if you drop an object, in the first chunk of time it falls 1 unit of distance. In the second chunk of time, because it's speeding up, it falls 3 units, then 5, and so on. Galileo was actually the first person to make quantitative studies of freefall, and realizing this elegant mathematical pattern was an absolute game changer in the history of physics.
Finally, Section 5, Physics Behind the Wheel. Equations that save lives.
Let's take these abstract laws out of the textbook and drop them right onto the highway to understand the physics of driving. Before your foot even thinks about hitting the brake pedal, there is your reaction time. It's a vital delay, and you can actually measure it at home using a super simple ruler drop experiment. When something demands immediate action, say a kid runs into the road, your brain takes time to observe, process, and act. That elapsed time is your reaction time. And when you're in a moving car, those tiny fractions of a second matter immensely. So how do you measure it? Well, because a ruler falls at the constant acceleration of gravity, the distance it slips through your fingers before you catch it directly calculates your brain's processing speed. Your friend drops it, gravity pulls it down at 9.8 meters per second squared, and depending on exactly where you pinch the ruler, we can use our kinematic equations to find out exactly how many fractions of a second it took your brain to tell your fingers to close. Pretty cool, right? Okay, so you finally hit the brakes. What happens next? The physical stopping distance of your car is dictated entirely by our third kinematic equation, and it's governed largely by your initial speed. If we take that third equation, realize that our final velocity has to be 0 because the car is coming to a complete stop, and we solve for distance, we find something crucial. The stopping distance equals the negative square of your initial velocity divided by twice your braking deceleration. Now, this is absolutely critical because that velocity is squared in the formula. Doubling your initial driving speed doesn't just double your stopping distance. No way. It actually multiplies it by a terrifying factor of 4. The real-world implication of this is massive. If you're doing 20 miles per hour and you speed up to 40, your car doesn't just need twice the room to stop. Because of the math of constant acceleration, it needs 4 times the room. And this single fact transforms these kinematic equations from some dry classroom exercise into the exact life-saving science used to set speed limits in places like school zones. When civil engineers are planning road safety, they rely entirely on the exact rectilinear motion formulas we've been unpacking in this explainer. They literally have to account for both human reaction time and the unforgiving math of that squared initial velocity to make sure cars have enough physical space to stop before a tragedy happens. So as you head out into the world today, I want to leave you with this final thought. Knowing that doubling your speed quadruples your braking distance, would your personal reaction time actually keep you safe on your drive home today? Look, whether it's the blood pumping through your veins, the earth rotating under your feet, or the buffer distance you keep between your car and the one in front of you, the rules of kinematics are always in the driver's seat. Thanks so much for joining me for this explainer, and keep looking for the physics hidden in plain sight.